Hello, welcome. This is Mr. Los. This is IB Chemistry Flipped Classroom, and we're going to talk about Lewis structures today. Now, a ton of stuff about Lewis structures was, or really covalent bonding in general, was pioneered by this man right here, Gilbert Lewis. Fantastic chemist and great name, Gilbert. Not enough people called Gilbert these days, if you ask me. So this goes along with the page in your workbook. I think it's about page 88 in one of the versions that I have, but it's in the bonding section. That might not be the exact page number, but you'll find it. So you do need to get that handy. You're also going to want a Lewis, a periodic table. But anyway, oh yes, there's our friend Mr. Cat. He's got a smile on his face, as I hope you do too, before we get started. So the page in the workbook you'll be wanting is this one, and you'll also want to have a periodic table handy. So let's remind ourselves really quickly of how to find the number of valence electrons for any atom. We count the number of columns across, not counting this middle section. So 1 valence electron, 2, 3, 4, 5, 6, 7, and 8, with the exception of helium, which only has 2 electrons, period. So helium has 2 valence electrons, and 2 electrons, period. What we're going to start by doing is draw what's called dot diagrams, Lewis dot diagrams for individual elements. And basically what these do is they show the number of valence electrons that a particular element has. So in the case of carbon, carbon has 4, as I just showed you there in group 14. So we would draw it like this. I'll draw it up here. We would draw a carbon, and what we would want to do is we would pretend sort of each side of the letter is an orbital that can hold 2 electrons, and also remember that electrons don't double up into orbitals until they have to. So carbon's Lewis dot structure would look like that, as opposed to, something like this, where we would be doubling up these electrons in these orbitals. Silicon, since it's in the same column as carbon, it's right below it, would have a very similar Lewis structure. Now, if we go back down, so the next one is nitrogen and phosphorus. Nitrogen has 1 more valence electron than carbon does, so it has 5. 1, 2, 3, 4, 5, and we could double that up at any one of those locations. Like, it doesn't matter where I put the double electron. Like if I do phosphorus down here right below it, 1, 2, 3, 4, 5. I could put the paired electron down there, just like that. What I would like you to do is see if you can go through and just really quickly draw the rest of these, see if we can figure out how those go, and we'll look back at that in a second. Okay, here we go. It should look a little something like that. That's what we're shooting for. Hopefully you figured those out. Now, where we're going to go with this is we're going to be drawing pictures of molecules, and I would remind you that we talked about the various atoms. What they strive to do is get 8 electrons in their outer shell like the noble gases. That's what they quote-unquote want. We wouldn't necessarily want to use the word want when we're talking about chemistry in particular, like in an IB exam, because atoms don't want anything, but it's definitely true that there's something about the noble gas pattern of electrons that is particularly stable. So these other atoms will do bonding to try to get these atoms like the noble gas. These other atoms will do bonding to try to get this electron pattern like the noble gases over here, so to try to get 8 electrons in their outer shell. An exception to that 8 rule is helium. Helium only has 2, and hydrogen also only quote-unquote wants 2, or is stable with 2 electrons in its outer shell. So keep that in mind. For most things, the thing that they want is 8. For the others, it is 2. So for the Lewis structures, again, we're going to be making a model. We're going to be making a drawing on paper of what molecules look like. And there's various steps, and if you follow these steps in a regimented pattern, step by step, you should be okay. And it takes a little practice, but hopefully we'll get good at it. But we're going to follow these steps. We're going to do these things in this order. Now, down at the bottom of the page, in your workbook pages at the bottom, I have separated out here. We have these steps listed, and then we're going to use these steps, and we're going to draw some Lewis structures. So the first one we're going to draw is F2. So let's go up to step 1 here. Count the total number of valence electrons. So fluorine has 7 valence electrons, and however, there are 2 fluorines, so we multiply that by 2, and we have 14 electrons to work with. So this picture that we're going to be drawing here in a second what must be true is that our picture must represent 14 electrons. This is true of all types of Lewis structures we will ever draw and is the most important step. Now when we look at step 2 here, guess the central atom, that doesn't apply to this one because there's only 2 atoms. That would only apply if there's 3 or more, so we're going to skip that one. We're going to go down to number 3. Connect each element to the central element with one line. Okay, well, again, there's only 2 atoms here, so we're going to draw an F and another F. That represents a bond between these 2 fluorine atoms, a covalent bond. So that's 2 electrons that they're sharing. And when we talk about the total of wanting 8 valence electrons, it's going to count as 2 for both of them. So as we make these drawings, we need to be very careful and account for all the electrons that we've used. We've used 2 electrons so far, and making that bond, that means my picture has to show 12 more electrons. So we basically accomplished step 3 here, and we calculated the new, we actually did step 4 already. So the number of electrons is 6 that are left over. So we're going to add these to the existing atoms as dots, and these represent electrons that they're keeping. So there's 12. I'm going to put 6 on both fluorines. 3, 4, 5, 6. Just kind of split them up evenly. And let's see what happens. We're going to go down to step 5. Now this is the critical step right here. Step 5 is the thing you want to check for whenever you draw Lewis structures. It must meet the bullet. Your picture must meet this first bullet. It uses exactly the number of electrons calculated in step 1, and then each element must have 8 electrons, including those they keep and those they share. You might want to add or make a little note here. If we're talking about hydrogen, hydrogen only wants 2. So be careful with that. Remember that hydrogen is an exception. But anyway, checking our Lewis structure here, we have 1, 2, 3, 4, 5, 6 dots, 7, 8, 9, 10, 11, 12 dots, plus this counts as 2, that's 14. So double checked, I did use the correct number of electrons. And then each element must have 8 electrons, including those they keep and those they share, except for hydrogen, which wants 2. Okay, so this fluorine is keeping 6 for itself, 1, 2, 3, 4, 5, 6, and sharing 2, that's 8. This fluorine is keeping 6 for itself and sharing 2, that's 8. So remember, this is a shared pair of electrons that counts as 2 for both. Now, it is also possible, and this is something you will see sometimes, to, instead of representing it as a line, you can actually represent it as dots as well, kind of in between them. So an alternative way to draw this Lewis structure instead of the line is like this. I will draw lines almost always, but sometimes you'll see it crop up where we have dots in between there. But anyway, either one of these are perfectly fine. If our drawing that we've made meets both these requirements, we're done and we can move on. And we are done with that one. That one is good. So let's do another example. I'm going to skip around and do a couple of these different ones. Let's do good old H2O, water. So start back from the top. Now, so we have H2O. Okay, so we're going to count up the valence electrons. Hydrogen has 1 valence electron, but there's 2 of those, so that's 2. So I'm just doing step 1 here. Oxygen has 6 valence electrons, so that's a total of 8. So I did my step 1. Now 2 says guess the central atom usually is the single element. So what I mean by that is these are going to be connected in some way, and almost always in these molecules what's going to be the case is there's going to be one atom and then other atoms are going to be connected to that one. So in other words, it's not going to look like this, it's not going to look like that. The atom that's by itself is usually the one in the center, and we're going to connect the other atoms to that one. So since there's only one oxygen, I'm going to put the oxygen in the center, and I'm going to connect the 2 hydrogens to them with bonds. So we've done step 1, we've done step 2, we kind of did step 3 there. So I've drawn 2 lines. That means 2 bonds. That means I've used up, out of my total of 8, I have 4 remaining. So now I've got to put those 4 electrons as dots on this for elements that still need more electrons for stability. So we're kind of working on step 4 here. Now one thing I could do is I could go ahead and throw all 4 of them here on oxygen. And the reason I'm doing that is because hydrogen, remember, hydrogen only needs 2 electrons for stability. It already has those 2. We're never actually going to add additional dots or anything to hydrogen. So going down to step 5 here and double checking everything I've done, it must use exactly the number of electrons calculated in step 1. Yes, it has. 1, 2, 3, 4, 5, 6, 7, 8. We very carefully kept track of that, and then also I just confirmed it and double-checked. Each element must have 8 electrons, except for hydrogen, wants 2. So oxygen keeping 4 electrons right here, and sharing 4. 1, 2, 3, 4. So oxygen has 8. Each of these hydrogen sharing 2. That's all they want. They're good. So we're done, and that is a good Lewis structure for oxygen. Now, there's a reason I drew it in this kind of bent shape, as we will talk about, as opposed to like in a straight line and all that stuff. We'll talk about that, but this is the main thing that we need so far. Okay, let's look at O2. Let's try to draw a Lewis structure for that one. So O2, we've talked about diatomic elements like the oxygen in the room exists as oxygen. So oxygen has, I'm going to go back to step 1. Oxygen has 6 valence electrons, but there's 2 of those, so we have 12 electrons. And using those 12 electrons, I have to try to get an octet 8 electrons around both of these oxygens. So moving on to step 2, central atom. There's no central atom here. There's only 2 oxygens, so I'm just going to connect those, and I'm going to have 10 electrons left over. Okay, so now I've got 10 electrons, and you know what? Let's just split them up. Let's put 5 apiece. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So we get down to step 5. And remember, our Lewis structure must meet these 2 requirements to be good. It does meet the first bullet. It uses exactly the number of electrons. We calculated that. My picture is showing exactly 12 electrons. However, it does not meet bullet 2. This oxygen here has 1, 2, 3, 4, 5 electrons that it's keeping. Sharing 2 is 7. Same with this other oxygen. So these oxygens are short of an octet. So therefore my Lewis structure is not valid. So for the first time we have to move on to step 6. You got to figure out the puzzle of how to get it to. You got to figure out the puzzle of how to get it to work out. And almost always when atoms are short of electrons, as they are here, the way to fix it is going to be to add multiple bonds. Atoms can share 2 pairs of electrons, a double bond. They can share 3 pairs of electrons, which is a triple bond. So what if I did this? What if I took away 2 electrons from my picture? Okay, so now I have 2 more electrons I could use and have those oxygen atoms share those instead. So notice I have not changed the total number of electrons, but now I am meeting the second bullet point here. Each oxygen has 1, 2, 3, 4 electrons that it's keeping, and sharing 1, 2, 3, 4. So keeping 4, sharing 4, that's 8. Each oxygen has 8 electrons. I've also used exactly 12 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so now my Lewis structure for oxygen is good. So that's the basic process. Let me do one more quickly. Let's do SF2. Okay, so we're going to go back to the top. We're going to go back to the first step. We are going to count the total number of valence electrons. So sulfur has 6 valence electrons. Fluorine has 7, but there's 2 of those. That's 14. And therefore the total is 20. So there's only 1 sulfur, so I'm going to put that one in the center, and I'm going to put the 2 fluorines on the sides. That's step 2. I've used up 4 electrons because I've drawn 2 bonds. Each of these is 2 electrons, so there's 16 left to go. Now, if you think about the fluorines right here, they already have 2 electrons. They're sharing 2. They're going to need 6 more electrons. So I'm going to put 6 electrons on this fluorine, and same with this one. So I've just put down another 12 electrons. That means I have 4 left to go. And I'm going to go ahead and put those 4 electrons on the sulfur, like that. And so now we examine my Lewis structure, and it does meet both of these points. It shows exactly the correct number of electrons. We kept very careful track of that here. But also, everything has 8 electrons around it. 1, 2, 3, 4, 5, 6. Keeping 6, sharing 2, that's 8. Same thing with this fluorine. Sulfur is keeping 4, sharing 4, so it has 8. So that's my Lewis structure for SF2. What I would like you to do is to try to draw these other ones. Now you might get stuck. There are a couple of tricky ones here. Remember, if you feel stuck or you get short of electrons, think about double bonds. Some of them might need to make double bonds. And then one thing we haven't talked about, well, let me just get you started on, for instance, OH-1 hydroxide quickly. It's the same basic process, but this one has a charge. So oxygen has 6 valence electrons, hydrogen has 1 valence electron, that's 7, but since it's -1 in terms of charge and electrons are negative, I need to add 1 to the total number of electrons, so that's 8. So hydroxide has 8 electrons to work with. That's the only difference between these ones down here that have a charge. With the NH4+, you would just subtract 1 electron. So anyway, go ahead, do your best, give these a shot. If you get stuck, you can move on, but give those a try and see if you can finish drawing those. Okay, so what I'm going to do is, here's what these should look like. The number circled is the number you should have gotten in the first step for the total number of valence electrons. So if you did something wrong, double check that you did that correctly. Now I drew these in a certain shape for a certain reason, but you don't necessarily have to have these in this shape. Like if you have, for instance, on this one, if you have the phosphorus and like the 3 chlorine sort of coming out like this or something like that, that's fine. For now, we will talk about why these are these shapes in the future. Just make sure you have the right number of dots and everything, and the general kind of arrangement is correct. So I just want to show you what these look like. And if you've got these, maybe you've had chemistry before, maybe you had some experience with this, you feel good about it, that's fine. I'm happy with having you stop right now. But if you need a little more help, what I'm going to do is draw a couple more of these from scratch. CO2 is one that causes people some trouble sometimes, and maybe this one, I don't know. I'll do these two. But again, if you got them, you're good. You can turn this off. And thanks for watching. Otherwise, I will do a couple more for you. I'll do these two, PCl3 and CO2. Okay, so PCl3. So phosphorus has 5 valence electrons, and chlorine has 7. That's 21. So we got 26. That's step 1. So phosphorus is going to be in the center because it's the singular atom, and the 3 chlorines will be connected to that. I have used 6 electrons so far, so I have 20 left to go. Now to kind of plot this out strategically, I know that this chlorine has a single bond, all of them do, that's 2, so all of these are definitely going to need 6 more electrons to get to their 8. So I am going to add 6 electrons here as dots. Okay, so I just put another 18 electrons on there, and there's 2 to go. So the chlorines are all good. They're keeping 6 for themselves, sharing 2, keeping 6, sharing 2, keeping 6, sharing 2, 8, 8, 8. Now the phosphorus is sharing 2, 4, 6 electrons. It's sharing 6. It would like another 2 to get to its 8, so those 2 electrons I have remaining, I'm going to put right there, and then my thing meets both requirements. It uses up all the electrons, I've done that, and it also gets 8 electrons around everything. So that's PCl3. Let's look at CO2. So carbon has 4 valence electrons, oxygen has 6, but there's 2 of those, that's 12. That means I have 16 electrons to work with. So I'm going to put the carbon in the center, I'm going to attach the oxygens to that. And that's 4 electrons I've just used, and I have 12 to go. So we could try a couple different things, like, okay, well maybe I'll put 6 electrons on each oxygen, like that. So when we talk about our kind of step here, this does not meet both of these requirements in number 5. It meets the first bullet, it uses all the electrons, but the carbon is short. The carbon here only has 4 electrons, 2 here and 2 here. The oxygens are good, they're keeping 6, sharing 2, but the carbon is way short. So when you're short, what you probably have to do is add more than 1 bond. So for example, if I erased 2 electrons there, so now I have 2 more electrons I could put on my picture, I can make a bond. Now, this oxygen is still good. It's keeping 4 electrons, sharing 4. It has 8. This oxygen is still good, keeping 6, sharing 2, 8. But the carbon is still short. It is still short of electrons. So what I'm going to do, I'm going to do that same trick again over here. Erase 2 over there, make another double bond. So now this is the correct structure. Oxygen keeping 4, sharing 4, that's 8. Keeping 4, sharing 4, that's 8. The carbon is sharing 8 electrons, 2, 4, 6, 8, so it has its 8. So that's the good Lewis structure, and that's really the only way you can draw it that meets both those requirements of those bullets in step 5. So hopefully that made some kind of sense. If you have questions, we'll definitely be doing this in class, a bunch more Lewis structures and all that kind of stuff, so we will talk about it. But hopefully you're on the track to being able to do these. Thank you as always for watching, and have a good day.